Good afternoon, everyone. Today, we like to talk about how we can execute a message on the destination side inside OffRamp. So basically, it's going to take 5 steps. The first step is we are going to validate and make sure the message is actually a correct message. It's not going to be a fake message. It's a real message. So it's going to verify its origin, integrity, and make sure the message has never been executed. You don't want to repeat the execution. The second one is it's going to handle the token. So if there's a need to do a token transfer, we understand in the source chain, we're going to burn or lock it. And then in the destination chain, we are going to release or mint it. Either way, it's based on the implementation. Because CCIP is a framework, so you still have some customization you can do according to a particular application. And then the third one is message invocation. So this is essentially, it's going to call the recipient, which is specified in message with the call load data encoded in the message. So essentially, it's a remote. You can consider this is like remote invocation. That one contract in the source chain can call a method or function in the other contract. So, so message invocation basically is remote procedure call or remote function call, and they also deal with the error handling. If one of these fail, either your token handling is fail or the remote invocation fail, remote procedure call RPC fail, then it's going to revert. And finally, either way, either the message is executed successfully or not successfully, you have to mark what is the final state of the message. Okay, so if you look at this, we are talking about OffRamp, and there are several functions involved in OffRamp that can facilitate the execution of a message. And in particular, we talk about two things they have to do for each message. One is going to release or mint the token, and that's performed by the pool. Okay, so by pool V1. The other one is it's going to call the receiver, which is RPG contract on the destination chain 2 with a call load, with a call data. Okay, so that's not in one of the contract. That's like application level contract. So any contract you can call from chain 1. So the call graph of execution actually start with either you can manually execute or you can execute by the transmitter. And we talk about transmitter is a group of people in the DAO network. So what is the DAO network? Basically, just a bunch of people maintained in the OffRamp as a data structure. So there is a list of signers, which is going to sign the message root and then commit it. And then the other group is a set of transmitter. Basically, they are executors. You can consider the transmitter is like the executors. So they are responsible for executing the commit functionality as well as the execution functionality. So there are two ways to execute, either manually or execute. And usually this execute will be done first by the transmitter. Only if fail, you have to do it manual execution. And the executor can be performed by transmitter only, but manual execute you can perform by anybody. I think that's just the design of the OffRamp. Probably it's going to give incentive whoever want to volunteer to do a manual execution, they will get rewarded. So manual execution probably is for message which failed the previous execution before, or for messages that nobody want to execute and it's been in the system for a while, then anybody can pick it up and execute it. And then all of this is all the way down here. I'm going to explain this picture later. But essentially, it's all boiled down to execute single message, okay? And this is basically allow you to do a batch execution. So the execute single message, as we said, do two things. One is release or mint token. The other is, do the execution, to the remote procedure call. So you're going to call the receiver with the method called CCIP receive. So the receiver, which could be any contract, must implement the interface, have the function called CCIP receive. So you can imagine actually in the source chain side, you also have application. We can call this a CCIP application. By CCIP application, what I mean is they support two functions. One is CCIP send, the other is CCIP receive. So this should be one function for the for this router in the source chain, and then in the destination chain, whatever contract is supposed to be receiver must also implement CCIP receive. Okay, so let's dive into the code to understand how manual execute and execute is going to work. As you can see over here, both of them is going to use the batch execute. So let's see what their difference is going to be. Okay, so let's go there. So the manual execution right here. So there are two methods. One is, you can consider this is more or less like automated execution. This is manual execution. Manual execution is going to check, if the blockchain has not been forked. And then it's just doing iteration because the argument is a list of reports. And each report is from one source chain. So different report might be from different source chain. And then within each report, there's going to be a list of messages. So you can imagine there are going to be two nested for loop. This is iterate through all the reports. This iterate through all the messages within one report. And then in one report, you can also doing a so-called gas limit overrider, because in the message the sender already specify what is the gas limit, but maybe the gas limit is too low, then the manual execution can override it. So this is the gas limit provided by the manual executor. Okay, so probably the manual executor is going to get compensated. Like he's not going to just provide the gas for free, right? So, but that's not shown over here. I don't know where that code is going to be, but from what we can see over here, anybody can execute this. So the overrider, they are just checking the override, the number of overrider is equal to the number of message, because each message needs one overrider. And then this is trying to check if the overrider is not empty, because you can also provide empty override if you want. Then it means you are not going to override. So, but if you do provide override limit, then obviously it has to be greater or equal to the original one. Otherwise, it doesn't make sense. So they have this check over here. And then in addition, they also are checking, because the limit is not only for the execution, but it also for the token transfer. So it's another check for token transfer. The token transfer is specified in called token amounts, which inside tell you, so each message can transfer multiple tokens. So token amounts specify which token you want to transfer and how much you want to transfer. So they are checking the override for the token transfer as well. Make sure if you do want to override, then it's going to be either equal or greater than the original one. So once you have doing all the checks, so this is basically doing just validation, make sure the second argument is going to be correct, and the override is going to be greater than the original one, or at least equal. So that's very much manual SQL is doing, just checking the gas limit is reasonable. And then the automated execution, on the other hand, is no override. But in order for them, both of them to enjoy the common batch execute, they provide empty override here as well. Just a placeholder, so that you can use the same common batch execute. In addition, they have a transmit. You don't have a transmit for manual execute over here. So this transmit is actually doing, is not going to check the signature. As you can see over here, they just provide empty signature. So then what is the transmit doing? Well, nothing. It's actually just checking inside, checking the function is called by the transmitter. In other words, this is like a authorization to just make sure not everyone can call this function, only if you are a transmitter specified in the DOM network. All right. So if you want to understand better about how transmit works, watch my video regarding the commit, the message route, and then there we talk about how transmit is going to work. Today we're going to skip the explanation of this function. You can go back there. So what is batch execute? Easily, it's just an iterator that allows you to execute a single report over here. And one thing you notice is they are doing override processing over here, because if there's no override, then this array is actually empty. So then, retrieving the override for this element, this one will not make sense, because you cannot specify which element. So what it's doing is it's just doing a check. If the argument of override is given is empty, then we simply replace it by another placeholder. So it's essentially reduced the dimension from two-dimensional array to one-dimensional array. So giving a two-dimensional array which is empty, I replace it by one-dimensional array with empty, so I don't get into out of bound as failure, because this element index is not make sense. So let's look at how we can execute one single report. Okay, so right now we are going all the way down. We explain these two, and then batch execute, it just iterate through each report. And then let's look at how we can execute a single report. Execute a single report, you can imagine it's going to iterate through all the messages, right? Because each report is all from one single source. So we retrieve this source chain number. And then the first thing we do is we're going to check if the source chain is actually cursed. If it's cursed, we are going to either skip it or we are going to revert. For the manual execution, we don't allow any failure right now. We don't allow you want your manual execution to be as smooth as possible. So so it's going to revert. Okay. Otherwise, if it's automated execution, we don't revert. We simply skip. So this is just either way. You skip or you revert based on its manual execution or non-manual execution. So if it's then we continue and check that we're going to check how many messages we have, and so this is checking the number of message, and then compare that to the length we specified in report. So report specify this is how many messages we have, and then here we count it and just make sure these two numbers match. And then otherwise, we are going to continue to reconstruct the Merkle key root. We want to make sure these messages are actually not touched. Their integrity is ensured. So we are going to create a bunch of leaves, and then basically we are going to be working like reconstruct the. So we are going to reconstruct from the leaf all the way here. We calculate the leaf hash for each leaf over here, and then 2 by 2 we combine until we all the way go back to calculate the leaf. Okay, so so we calculate the leaf, and this is how we calculate it basically. Which is right here. I already have it. So basically, this is how you calculate hash. There are two parts you need to consider. The first part is they call mat hash, which is right here. So you have the prefix, it's a fixed number, and then we encode a chain selector, and then this is basically destination chain. This is a source chain, and then we also put the source chain on ramp address over here. Okay, so that's actually for every single message. So this is why it's one of the meta hash over here. That's why it's called meta hash, because it's a data hash for all every single message. And then this is a message specific information, the message ID, who is the receiver, who is the sender, what's the data over here, what's the token transfer information, including token number and amount, and then also the gas limit specified by a regional one. Keep in mind, we don't use the overridden version. We have to use the original version, okay, to and tempering, right? We are checking the original message, not the new gas limit. So I also look at the header nonce, which is used to control the execution ordering, and then the sequence number, which is the message number, and the receiver. So you can compare these with the original message signed by the source chain, and these two have to match, right? Whatever containing original message, we bet contain over here, so that nobody can change the message, basically. So that's very much the hash that we put over here. And of course, they also doing a little bit check of the header to make sure the message header is correct, which is message header destination chain selector. Destination chain selector over here. Okay, so they are going to make sure chain selector is going to be equal to destination selector. So no wonder over here we didn't have the destination chain selector, because it's already equal to these check. So if they're equal, they're already included, right? So that's another thing we have to be careful over here. And then source chain selector equal to the header. As you can see, we include the source chain selector over here, right here, source chain selector. This source chain selector, which is we retrieve it, it's right. Let's just double check, over here. So it's a report source chain selector. So it's already included in the hash as well, both of them. And then after we have done that, we call the hash, okay? And we already show you the hash function. So it's going to be stored in the hash leaves array. And then we're going to call the verify to make sure the verify is going to return the root, I'm sorry, the timestamp that the root is committed. So we can take a look at how it looks like. It's over here. So it's going to call the Merkle multi-proof utility function called Merkle root, which takes 3 arguments: the leaves, and then the proofs, which is part of the message you provide offline, and then proof flag bits to guide how the proof should be used. Essentially, tells you the information, which tool should be combined to calculate the parent. So this supposedly is going to return the root hash, and then remember, in the commit phase, the root is already committed, so the timestamp of the commitment is stored in this mapping, and we retrieve it. So supposedly it's not going to be equal to 0. If it's equal to 0, then that means it's not committed yet. So then we cannot execute it, because that means this message doesn't belong to a committed tree over here. Each root represents a tree of messages that have been committed. So we retrieve the timestamp equal to 0, we revert. Otherwise, we're going to execute the message. We're going to iterate through it. First of all, we're going to retrieve the original state of the message. Okay, I'm not going to get into this function. So you might take a look how this function is implemented. So you get the original state, and this basically says the original state have to be either untouched or failure, and nothing else. Okay, you start from either untouched, means never executed yet, or you executed before but failure. So this is only 2 things that we allow over here. And then otherwise, we are going to skip. So in other words, if the source state is not involved in this, then we are going to skip it. So this is actually true for either manually or the manual. And then next one is only for the manual one, manual execution. The manual execution is simply say either the message is committed long time ago. So this basically say the message is committed long time ago, then we can do the manual execution. Or the original state is failure. That means you tried before by the automated execution, then we can do a manual execution. Otherwise, we cannot do the manual execution. Okay. And then there's also overriding guess limit over here. We are checking if there's overriding, because only when you do a manual execution, you can do the overriding. Okay. So that's done here as well. Otherwise, if it's the automated execution, then you can only start from untouched. Okay. Once you touch it, you cannot do automated execution anymore. So that's the only case that's allowed. So if it's already touched, either it's a failure or successful, you cannot do it again. We just skip this message. And then the next thing is to make sure sequential execution will be honored. So how do we know the message needs to be, the order needs to be enforced? They check the nonce. If a message have a nonce, that means you have to execute according to the nonce number. Otherwise, you don't need to worry about this check. So this check is only check once, only when the message is untouched. So either manual execution or automated execution. So then you're going to increment nonce by, if it's not checked, you're going to increment nonce by 1. Okay. And then the nonce manager might increase or might not. It depends on if it's going to match or not. If it's going to match the nonce number given, then increment will be successful. Otherwise, it's going to fail. But either way, we're going to continue. So Oh, I'm sorry. If it fail, in other words, the nonce is not incremented because when it's tried to increment, it's not equal to the expected nonce. That means this message is out of order execution. We don't execute an out of order execution over here. We are simply going to skip this message. We don't want to execute a message out of order. So we continue. This is interesting over here because usually for manual execution, we are going to revert. But this is probably one of the very few cases in which we still continue to execute subsequent messages, because from other places I see manual execution is always do not allow any failure at all. So this is an exception. We have to keep that in mind. And then we continue over here to we're gonna check the number of token we want to transfer is equal to of chain taken length. So this is just a checking over here. And then so these two has to match. And then they are going to set execution state to in progress. I believe it is to ensure no reagents attack. And then they will try to execute the message. Okay, I will explain this in a little bit later. So once you execute finished, you are going to get a new state, regardless what's going to happen inside. Okay, and then the state will be set as the new state of the message. So previous state is in progress, and this is going to be the final state. And then in the middle, you try to execute the message. Okay, and then there's also a post checking over here. So this is just checking if it's manual execution. We need to make sure progress will be made. In other words, either it's going to be from untouched to failure, or it's going to be from untouched to success, but it doesn't going to be allowed from failure to failure. So if the original one is a failure, then you bet the original one has to be untouched. Otherwise, you're going to revert. You bet the original one is untouched, exactly. On the other hand, the final state has to be either success or failure, nothing else. That's another check over here. Okay, so so that we are actually, this kind of a check for the state is going to ensure it's going to have the correct transition. You don't allow illegal transition. So it's actually implementing a state machine. So it might be helpful for draw a state machine in the beginning. I'm not going to explain this, but I think in the source code they kind of explain. Do they explain over here? Oh no, they don't. Okay, so so we are right here now. We execute a single report. So and then basically we go through each message one by one, try to make sure the message belong to the tree. The root has been committed, and then now we are going to execute each message by calling the trail execute. So what is the trail execute look like? Trail execute turns out is just a wrapper to call try execute single message. So why do we need a wrapper over here? Because what we are going to do is the execute single message is going to be executed in its own execution environment. In that environment, and we'll either revert the whole thing. In that case, we are going to catch the error and then return the failure. So that means when the execute message fail, it's not going to change the state. No state will be changed inside that context until we simply say we return failure over here. On the other hand, if it's successful, then of course all the states changed by execute single message will be persistent. and then we're going to return success. So this wrapper is very important. It's going to make sure, regardless SQL single message is successful or not, this child SQL will always be successful. So you're not going to revert child SQL. You only revert the inside one. So this wrapper is very important. And in addition, why we didn't encode this as internal message, we are calling this anyway. As a matter of fact, this SQL single message can only be called internally. So one question is why we do that. Well, the reason is because we want to do try catch over here. So if it's internal, then the internal function will be executed in the same context. But if I execute this is external, then it's going to be a separate execution context. So basically, it's isolation of execution contexts. So in this way, we can use a catch and a try to process the output of the execution of another function, which is totally in a different execution context. So let's go to the execute single message. So this is declared as eternal, but don't expect you're going to call this by anybody. As you can see, it's actually considered like an internal function, but we have to keep the external because we want to use a try and a catch. And then the first thing, there are two things done by this function. It either release or min a token, or it's going to call the receiver CC receive. Okay, it's going to either call the over here. It's basically called the receiver side CCIP receive function. That's only two things done by executing a message, and that's what it means. Also, executing a single message means two things: you send a token, you call the receiver CCIP receive. Okay, so first thing, let's look at the first one. It's going to call release or min token. The input is token amounts, which means for each token how much you want to transfer, and then it's going to return another array destination token amounts, which is also how much token for each token, how much is transferred successfully. And these two might match, might not match, because it depends on the protocol, because some of them might charge you some fee. So this could be less than the input, okay? So that's really application specific. So let's look at how the release or min token is performed over here. As we talk about, it's going to call the pool to do it. Okay, OffRamp is going to interact with the pool v1 to do the mint or release. So the first thing is going to create the return array, which is going to be exactly equal to the number of token you have in the source token amounts. And then we do an iteration over here. And then if we do need to override for the manual execution case, then we're going to override it, because for every token transfer, we specify the gas limit. So the gas limit will be overridden right here. And then after we prepare for this, then now we can call the release or min single token to do the real thing. And this one, essentially, it's going to based on the local token, it's going to look up in the token admin registry. Let me see, do I have that over here? Yeah, token admin registry. So token admin registry, just do a lookup, because for each token, they might use different pool. So that means this the pool v1 is not just one contract; it's a bunch of contract. Different token might use a different pool to do it. Okay, so do a lookup in the admin registry, get the pool address, and then make sure the pool address is not zero, means it exists. and then support the right interface, then now we can call it. Okay. Before we call it, we want to remember we need to return the for each token we need to return how much token is really transferred. So this is going to check. We do a before balance check and after balance check. So this is a before balance check, and then it's going to call a low-level function. This function is very interesting by itself, but I'm not going to talk about today. You can look at this function by yourself. This is basically a utility function to a low-level call the pool. Basically, call this function with all these arguments. But the reason they use a low-level call is they want to prevent malicious pool, because as we talk about, the pool can be customized, can be provided by a particular application. So this call make the low-level call very safe in two things. Number one is they are going to specify the gas is going to be exactly going to be the gas used. You cannot use too much gas. So in other words, this is like slippage control for the gas fee. And then there's also a slippage control for the return data. So these two make sure that you are not going to have a malicious pool who is going to consume a lot of gas, or who is going to return a huge return data, so that it's going to consume your gas when you try to copy the return data. Okay, this is so-called, I guess, gas bomb attack. Okay, so in one word, this low-level call is to prevent gas bomb attack. But the real thing it's done is simply call pull, release, or mint. Okay, which I draw over here. So it's called release or mint token. It's called release or mint single token. Because you might transfer multiple token, and each single token transfer is we are just going to call it pull, release, or mint, using low-level call to prevent gas bomb attack. Okay. If it's not successful, it will revert. But keep in mind, the outer wrapper is going to catch this revert and just say, well, execution failure. And then it's checking the return data length is just 32 bytes. It's just one word. Okay. And then make sure it's one word. Then we are going to decode it. This is the amount of transferred token, or release a token, or mint token. And then we do a after balance check. The after balance check, make sure it's going to increase, not only increase, but also the amount increase is equal to local amount, which is encoded in the return data. So this local amount might be, as we talk about, it might be smaller than the input local amount. So because they might charge some fee over here, the pool might charge some fee. But anyway, you have to be consistent, because you tell me you're going to return this me. I do a balance check, make sure that my balance indeed increased by this amount that you tell me this is how much you transfer to me. Okay, so that's how it's done by release or mint one token. Okay, over here. And then once we iterate through all the token, then the array will be ready to be returned, because now you know for each token how much real amount of token is minted or released. Otherwise, once we release our token or mint our token, now we are ready to do the execution, to do the remote procedure call. Okay, RPC. Let's call that RPC. So now we are able to do RPC. Okay. Now let's resume the execute single message here. We are done with the release all the tokens. We return an array of all tokens release or minted. Then now we are going to construct a client message. The message is called any to EVM message. So this is going to contain the message ID, the source chain selector, the sender, message data, and destination token amounts. I'm sorry. So yes, and they also allow a customized the interceptor video, which is you can construct this message, including the message ID, source chain selector, the sender, the data, the destination token amount, and then send it to the interceptor. Okay, what the intercept is going to do is depends on the application. So application can customize this protocol. You can consider this like plugin. You can customize this plugin and to deal with the internal logic of inbound message over here. Okay, so and then next one is do the remote procedure call. Okay, so one thing to check is we're going to check the message gets limit is equal to. So they are going to check that the message data length is not equal to 0. If this is equal to 0, we are going to return. And if the code length is equal to 0, we are also going to return. If it doesn't support the interface, we are going to return. So the remote procedure call will not be performed, but over here, see so this is more like optional. Okay, this means if these constraints are not satisfied, we don't revert. We simply skip the remote procedure call. Okay, so we need to keep this in mind, and then otherwise, it's going to be load message through the loader. Okay, and the load message is simply do the remote procedure call through the loader because only the loader know how to which receiver to call and so on. So let's look at this. Okay, and over here we see this is a receiver we're going to call, and this is the gas limit that's provided. So we have to make sure the gas limit is not equal to 0. If it's equal to 0, that means we don't have gas to do anymore, and then we have to return. So let's look at the loader. Okay, let me go there now. I don't have the loader with me. Okay, so let's look at loader message. The loader message is going to check that the caller is going to be OffRamp, basically, and then it's going to do a low-level call again using this nice low-level calls. It's called exact gas, so it's not going to use too much gas, and then also going to use a save return. So it's going to call exactly the receiver, and the data is prepared by this, so it's going to call CCIP receive using the message is the call data. Okay, using that, which is any true EVM message. Okay, and then otherwise it's going to be returned, right? So it's so this is executed by the reader. I'm just wondering why we cannot implement this inside OffRamp. I think we why not? Probably we could, right? I mean, I don't see any reason why load message cannot be implemented directly inside OffRamp, as far as I can see. But probably they have their reason over here. Maybe in the future they're going to introduce additional logic in the load message, maybe some other check over here, and so on. But anyway, they don't call. Yeah, I think that might be a good idea. So they don't call directly. They just call through the load message, essentially routing, as the name suggested. They will use the router to see which receiver to call. But that receiving information is already in the OffRamp. So anyway, that's important. So over here, once the message is routed and executed in the receiver side, then it's going to either successful or failure. It's going to return, and then this will be captured by the child execute, which either is going to say the execution is successful, change the state, or it's failed. So in conclusion, the client side chain one is going to call application level. Any object contract can call the CCIP router, the router. So we have a router over here. We also have a router over here. So everything is through the router. So the router probably serve. Yeah, I think that might be a good abstraction. The router serve as the entry point for application. So the client side, you call the router. The server side, the router will call the application. Yeah, I think that might be a good way to think of it. And then the destination side is going to iterate through all the reports, all the messages, and for each message, it's going to try to execute it, either successful or failure, and then record the state. All right, so that concludes our presentation for the message execution. Hope you enjoy it and learn something. Have a nice day.